November 7, 1940. 10 a.m. A newspaper editor named Leonard Coatsworth is driving across the Tacoma Narrows Bridge in Washington state. In the back seat, his daughter's dog, Tubby. The bridge is moving. That's normal, this bridge always moves. Locals call it Galloping Gertie. Drivers pay the toll just to feel the road roll under them like a slow ocean swell. But at 10 a.m., the motion changes. The deck stops bouncing and starts to twist. Within minutes, the roadway is tilting 45 degrees, one lane rising 8 meters above the other. Coatsworth abandons his car and crawls to safety on his hands and knees. Tubby, terrified, refuses to leave. At 11 a.m., the center span tears itself out of the sky. Your physics textbook told you why this happened. Your textbook is wrong. To understand what killed this bridge, you need to understand what made it beautiful. 1940. Suspension bridges are the pride of American engineering, and Leon Moisseiff is their prophet. Moisseiff championed something called deflection theory, the idea that a suspension bridge's cables carry so much of the load that the deck itself can be light. Slender. Elegant. Cheap. Where other bridges use stiffening trusses 8 meters deep open lattices the wind could blow straight through, Tacoma got a solid plate girder just 2.4 meters deep. A ribbon of steel. Here are the numbers. Main span, 853 meters, the third longest on Earth. Width, 12 meters. That's a width-to-span ratio of 1 to 72. The Golden Gate is 1 to 47. Nothing this slender had ever been built. And from the day it opened, July 1, 1940, it moved. Vertical waves rolled down the deck in a gentle breeze. Engineers were worried enough to study it. But vertical bouncing, it turns out, was never the danger. For 4 months, Gertie galloped and survived. Because the killer wasn't the bouncing. The killer was waiting for the bridge to learn a new way to move. Open almost any physics textbook and you'll find Tacoma Narrows in the chapter on resonance. The story goes like this. The wind blew across the deck and shed vortices, little spinning whirlpools of air, at a steady rhythm. Each vortex gives the deck a tiny push. And the story says that push rhythm happened to match the bridge's natural frequency. Push a swing at exactly the right moment, every time, and a small force builds a huge motion. Resonance. Case closed. It's a beautiful story. It's in textbooks, in encyclopedias, in physics lectures at great universities. And it fails the most basic test an engineer can apply. Check the numbers. Vortex shedding has a rhythm you can compute. It's set by the Strouhal number. Shedding frequency equals Strouhal number times wind speed, divided by the depth of the body. Plug in that morning's numbers. Strouhal number for a bluff section like this, about 0.11. Wind speed, 19 meters per second, a 68 km per hour gale. Girder depth, 2.4 meters. That gives a shedding frequency of roughly 0.9 Hz, call it 1 push per second. Now, the frequency the bridge was actually twisting at that morning? 0.2 Hz. 14 twists per minute. The push rhythm and the motion don't match. They're not even close, they're off by more than a factor of 4. Resonance needs the hammer to strike in time with the bell. This hammer wasn't. The textbook story is dead. So what actually killed it? Something far stranger than resonance. The bridge didn't need the wind to push in rhythm because the bridge created its own rhythm. The motion itself generated the force that amplified the motion. Engineers call it aeroelastic flutter. Here's the equation of motion for the deck's twist. Inertia times angular acceleration, plus damping times angular velocity, plus stiffness times the twist angle equals the aerodynamic moment from the wind. Normally, damping is your bodyguard. Every cycle of motion, it bleeds energy out of the structure as heat. Amplitude dies. But the aerodynamic moment on this deck had a component proportional to the twisting velocity pushing in the same direction the deck was already turning. Look at that damping term now, C-A. The H-shaped girder was so aerodynamically vicious that it grew with wind speed, and on November 7, at 19 meters per second, it became bigger than C. Total damping went negative. Negative damping means the bodyguard has switched sides. Every single cycle, the wind deposits more energy into the twist than the structure can dissipate. The amplitude doesn't grow linearly, like resonance. It grows exponentially. Each swing bigger than the last, forever, or until something breaks. And the frequency it locked onto was the deck's own torsional mode. 0.2 Hz. Not the wind's rhythm, the bridge's. Flutter doesn't ask the wind to keep time. It only asks for enough wind. On the bridge, this took about 70 minutes from first twist to failure. The motion sawed at the midspan cable bands until one slipped, feeding the torsion even harder. Hangers began to snap like guitar strings, one by one, each failure loading its neighbors. At 11:02 a.m., a 180-meter section of roadway tore free and fell 60 meters into the Narrows. Tubby the dog was the only life lost. A professor had crawled out to save him. Tubby, in terror, bit him. He fell with the bridge. No people died that day. What died was an idea that a bridge could be designed by gravity alone, and the wind would forgive it. The wreck of Galloping Gertie changed engineering law. No major bridge is built today without wind tunnel testing of its deck section. Its replacement, Sturdy Gertie, got deep open trusses the wind blows straight through. It's still standing. The number to remember, 0.2 Hz. The bridge's own torsional frequency, the rhythm it was always capable of, waiting for a wind strong enough to flip its damping negative and let it sing itself apart. Every disaster is a physics problem someone got wrong. Next time, a hotel walkway in Kansas City, one change drawing, and the simplest free body diagram that ever killed 114 people. Subscribe and check the numbers.